Okay, good morning all. Uh, we start. So I welcome you to the fourth lecture in the mechanics of material. And today we are going to find normal stress and strain and stress strain diagram. Okay. So yesterday we have covered very important part and we'll quickly revise that. So this blue color indicates a body which is elastic body. Elastic body means any material uh, which is a component of some machine or some structure, and the loads are being applied on this body. So this is general representation of any component, any part of a machine which is subjected to load. Now the load can be anything like tensile load, compression load, bending, torsion, shear, any kind of loading. But this represents that this blue color represents a body, a component, a material which is subjected to different kinds of loads. Mostly this is a elastic body. Okay, so by elastic body we know that elastic body or elasticity property is such a property that when load is applied on the elastic material, it deforms, and when the load is removed, it regains. So when it regains, that means there is something inside the rigid body, elastic body, which is causing this body come back to this original position or original shape. And these are very important parts. These are called as internal resisting forces. So the important thing to understand here is, first, the loads are applied. Second, the deformation of the elastic body takes place because of its elasticity. And then to oppose this deformation, internal resisting forces set up. And these internal resisting forces are in such a way that they oppose this deformation and they are equilibrium with this external forces. Okay, so this internal resisting forces is very important for us because we are going to deal with them a lot. Now how to define them, internal resisting forces. Okay, so what we have done here is we have taken a body, we have taken a section, and then we have considered a small area dA or delta A, and on this area what is the total resisting force that is generated, that is represented by this vector delta F. Okay. So we have considered a small area, and on this area the net force that is generated inside the rigid body, inside the elastic body, that is delta F. Now this delta F is a vector in 3 dimension, so we can take a resolve this force into x as delta Fx, in y as delta Fy, in z as delta Fz. So these are the 3 resolution of this force delta F, which is the internal resisting force acting on this area. This blue color is the area, small area we have considered in this section, and then we are considering this delta F as the internal resisting force. Now, if we consider this delta Fx, delta Fy, and delta Fz, we'll understand some things. The first thing that we understand is this delta Fz is acting perpendicular to this area. So if you consider this area is in the Z plane. So how do I say Z plane? The plane which is perpendicular to the Z axis is called as Z plane. So here is a plane, Z plane, which is perpendicular to Z axis, and this Fz is acting perpendicular to that area, perpendicular to the Z plane, and this blue color indicates the area on which this force is acting. So this Fz is acting perpendicular to this area, while if you consider this delta Fx and delta Fy, they are acting in the plane, in the same plane, in the same area in which the resisting area, the area under the consideration. Okay, so what we try to do here is we try to find the average force. So what we do, we take this delta Fz, then we divide this by the area which is giving us this delta Fz, and we try to find out this average. And what we do is we try to keep this area very small, then we get some quantity and we call that quantity as a stress. Stress has one more name. It is also called as intensity of stress. So this is also one name, not quite commonly used, but intensity of stress is also one name that is used. Now here we are using this nomenclature sigma zz. This first part indicates in which plane this area, this force is acting, and the second z is saying us about the direction in which it is acting. So z plane and z direction. So here you can see this plane is z plane because it's perpendicular to the z axis, and fz is acting in the z direction, so it is z direction. So sigma zz. Okay. uh, this is a normal stress because this force is acting perpendicular to the this force is acting perpendicular to the area. So that's why we call this as a normal stress, and it is usually represented by the sigma z. The second, if you take delta fz, this is acting on a plane z plane. It is acting in the x direction. So we show this as a sigma zx, z plane x direction. And because this is a shear force or a shear stress, we represent this by tau. Tau is commonly used for all the shear stresses. So tau zx, z plane and x direction. And again, the definition is something like this: the force delta fz divided by delta a, where the delta is negligible, very small. Similarly, we can do it for tau fy, delta fy divided by delta a, limit delta a tends to 0. And sigma zy, we can say it as a sigma zy, or we can say it as tau zy. Okay. So these are the three stresses generated on the same plane, one plane. If you take one plane, we are getting three stresses: one normal stress and two shear stresses. Okay. So we moved ahead and we have taken one more section. Then there are again some internal resisting forces. We have done it for one more time, and finally we have got something like this, a cube. And in this cube, basically we have considered three faces, but all the faces are like mirror images of it. So all the six faces we get three stresses acting. Okay. But when I say sigma x is acting here, the same value of sigma x is also acting in the opposite direction. Okay. So that gives us this thing. This is called a stress tensor. Tensor is a term that is used when we want to define something which has a magnitude, direction, and also many directions, like not one direction, many directions, and we need plane to define that completely. So such a case, we use it as a tensor. You can read about the tensor much more in the Google. You will find many nice explanation for this, but right now stress is a tensor, and we need to define these values of stress. We need to define the direction, and we need to define the plane on which it is acting. So we need all this information to define this tensor completely. Okay. So totally on the first plane, we have sigma x, tau xy, and tau xz. On the second plane, we have tau yx, sigma y, and tau yz. And third plane, we have tau zx, tau zy, and sigma z. So out of this, these diagonal elements are normal stresses, and all other six elements are shear stresses. Out of this, this tau xy and tau yx, they have the same value. Okay, they both are equal. Similarly, tau xz and tau zx, they are same, and tau zy and tau yz, they are same. This is because of one principle. We are going to study that principle, but right now I will just give you the name. This name is called as complementary shear stresses. So because of that principle, complementary shear stress principle, these two are the same. So basically, out of this 9 component, 3 components are basically repeating again and again. So basically, when you want to define the stress tensor, you need only this 6 values: 3 normal stresses and 3 shear stresses. Okay. So this is what we have learned. Very important part in understanding this subject as well as aircraft structures, which you will study in the coming semesters. So remember this part. Okay. So when we are discussing about the stresses, there are basically two types of stresses we have discussed. One is normal stress, which is also called a direct stress. Normal stress is something, suppose this is the area we are taking under the consideration, which is offering the resisting force. This is a very important thing. This is the area which is offering the resisting force. And suppose the stress is acting perpendicular to this area, we call this as a normal stress or direct stress. And if it is acting in the plane, in the same plane of this area, we call this as a shear stress, which act in a tangential direction. Okay. So normal stress can be of two types: tensile stress or compressive stress. So first, today we'll discuss these things first. So today we'll try to focus on this. And next, in some upcoming lecture, we'll talk about the shear stress and shear strain. Okay. So normal stress is one which acts perpendicular to the resisting area. Shear stress is one which acts in the same plane. Okay, so here you can see this. So we'll talk about normal stress and normal strain. So first we'll talk about the tensile stress and tensile strain. Suppose if you take some bar of length Li and then you apply some load on this. So suppose some P load is applied. You can apply the load only when it is acting on the both direction. The case may be, it is represented something like this here as a free body diagram, but the actual case may be something like this. If you have a rod, you fix it at one end and then you apply the force at other end. So what this wall is doing is, wall is creating this resisting force according to third law. Unless this wall is creating this load, we can't apply this load here. So it is like this. This is basically the free body diagram for this. So we remove this wall and we put this force which is caused by this wall. Now we cut this. One more thing, and this is under the equilibrium. So if you consider this thing, this is completely under the equilibrium. This is a bar. This is the load acting in left direction, load acting in the right direction. And if you consider this, if you add these forces, you will basically get a zero. So one force is acting here, one force is acting in opposite direction. You take the vector addition of this, you get a zero. So we have seen this Newton's first law. So whenever there is a no unbalanced force, the body will keep on being in its position of rest or position of motion with a uniform velocity. So this is basically a equilibrium. When there is no unbalanced force, that is a equilibrium. So this is a equilibrium where the forces are balanced. Now you might have studied this method of section. Method of section says that when some body is in the equilibrium condition and if you break this body into two parts, that is also under the equilibrium. So we'll use that principle, method of section. And to do that, I will take this section MN and notice this, that this section is perpendicular to the axis of this bar, perpendicular to the axis of this bar. So when we have taken this section MN and now this force P is acting here. Now to balance this force or to make this body as equilibrium condition, because we know that the body was in equilibrium, so we have to replace this with this resisting force. So this is basically the resisting force which is generated inside the body, and this resisting force is actually equal to the applied load. Then only we will get the equilibrium condition. So we have taken a section MN and we see that there is a equilibrium force acting. So I have considered the right hand side. We can also consider the left hand side. Left hand side will look like this. Suppose this is a bar, this is a force, and then the resisting force will act in opposite direction like this. Okay. So when we have done this, what are the assumptions? Assumptions are like this, that this force P is acting along the centroid of this bar. So uniformly the force is acting and only force is acting. It is not creating any kind of a moment. The material is homogeneous. That is also one assumption we are taking here. So when we do this, we get tensile stress because we are dealing with the tension force. We call this stress as a tensile stress, which is equals to resisting force divided by area, which is equals to P upon A or R upon A. So we have done this calculation also. Next, tensile strain, which is represented by the symbol epsilon. Tensile strain is equals to change in some dimensions divided by original dimensions. Some dimension means here the important dimension is the length. Okay. So this rod is having the length and we are applying the force in this direction. So length is also increased, and the what is the change in the length is final length minus initial length divided by initial length. That is dl upon initial length li. So that will give us the strain. Both these are the units of length, so they cancel each other and we don't need any unit to define it. But sometimes in the practical applications, they might have like uh, millimeter per millimeter or millimeter per meter kind of a units used for some practical applications, but real life sorry, for actual it don't have any unit. So this is about the tensile stress and tensile strain. Similarly, we can get compressive stress and compressive strain. So we get a rod, we apply the force on this, we consider now the important change is the forces, resisting forces as in the opposite direction. Um, Compressive stress is equals to resisting force upon area. Compressive strain is equals to change in dimensions divided by original dimensions. Ignore the sign here. We'll only consider the change in dimensions. We'll not consider the negative or positive sign. We need the change in dimensions. So here it will be Li minus Lf divided is equals to dl upon Li. Okay, so this is about the compressive stress and compressive strain. Sometimes we use a negative sign to indicate compressive stress and use positive sign for the tensile stress. That is also fine. That depends on the numerical. I will explain you these things when we start solving the related numericals for this. So both of this compressive stress and tensile stress act directly perpendicular to the plane on which it is acting. So here we can see this. So they are called as normal stress because the force and the resisting force are acting in the perpendicular direction to the area under the consideration. Okay. Next thing is shear stress, but we will discuss the shear stress in detail in some other lecture. Now, next point is a very important point, that is stress strain diagram. So we have been talking about the elastic material and all these things. All of this, they have the material properties. They have their own properties of elasticity, strength, etc., stiffness. And we need the values of this elastic properties to find out to design something. So when we are designing, if I'm designing something with the steel, I must know what is the strength of the steel, what is the elastic limit of the steel and all these things. So those information we get it from the stress strain diagram. So to understand the stress strain diagram, we'll first understand what actually happens when we load elastic material. So here you can see this is basically the lattice structure. So in most of the crystalline material, we have a lattice structure. All the crystalline material will have the lattice structure. This brown color indicates your respective atoms or molecules, and they are very closely packed. Here, if you pay attention, you will see that they are very closely packed because there is an attraction force between the molecules. So suppose this is a molecule, this is the next molecule, and suppose they have cubic structure, they will have uh, the bonds between them, and these bonds will try to keep this two atoms very close to each other. So this force is always present between the two molecules, cohesive force that is present between two molecules, and that will try to keep these molecules as close as possible. Okay, this is the initial condition when no load is applied. So this is our component. This brown color rod is basically the component, and we are observing what is happening at the molecular level. So no load is applied. Just pay attention here. No load is applied. Just simple rod is there and no load is acting on this. When we apply this load F, what actually happens? You observe here that there is some gap that is created between these molecules. You can observe this gap. So what is actually happening is these bonds are getting stretched. Oh, so something like this becomes something like this. So this gap between the molecules has increased. But the important thing is molecule has not left its position. It is at its own position. You might have studied this lattice points and all these things in your 11th, 12th. So atoms, they have their lattice positions. So something like this. And here, this is the lattice position. It is the same lattice position. Here again, the same lattice position. But the only thing is the bonds are stretched and the gap is created here. Okay, there is one doubt. I will clear that doubt. I will read that doubt once again. Um, Resistive force and tensile force are in equilibrium, but the object will undergo some expansion or compression. If they are in the equilibrium, then there should not be any movement. So what I'm explaining is basically the same thing. What is happening is when the forces are applied. Okay, I will give you the example of spring. That will be a better example. Suppose this is a spring and no load is applied on this spring. Okay, so this is the position of the spring. Okay, so when you apply the load on the spring, what happens? The spring will get elongated. Okay, now this is the new position of the spring. So this is before application of the load and this is after the application of the load. So before the application of the load, the spring was in the equilibrium condition. After the application of the load, spring again become in the equilibrium position. But what has happened is, to oppose this applied load, there has some resistive forces set up inside this. And when this resistive force is set up, there is a deformation, because this resistive force is created because of the deformation. Okay, so same thing is happening here. So these bonds are getting stretched and then they are generating these resisting forces. Okay, but they are stretched. So you can see this elongation has been, this rod has elongated. Is it clear, Saurabh? So when the loads are applied, bonds stretch and then that cause the elongation in a rod. Okay, so I hope it is clear. So here you can see this delta. Delta is basically a small elongation that has taken place, and this load applied is also very small. Now if I remove this load, what is going to happen is, we know that already there is this resisting force present between the molecules, and when we remove this, this resisting force become higher and it will uh, pull these atoms back to its original position like this. So if you compare this thing with this thing, you will see it is exactly the same. And also when you see this delta, it's completely gone. So the rod has completely returned to its original position. Okay, so rod has returned to its original position and we experience this every day. So we have something, we apply the load, it elongates, and then we remove it, it goes back to its original position. So same thing is explained here in different diagrams. That's it. Now this is about the small load up to the elastic limit. So this thing will happen up to the elastic limit. But what will happen if I keep on applying the load beyond the elastic limit? So this thing will happen. So initially it is same thing. Molecules are closely packed at its own lattice positions. We start applying the load. Initially the elastic load, elastic deformation will take place. That part is missing from this diagram. So I will explain it here. So suppose this is a molecule, this is next molecule, this is, I will just take 4 molecules. So suppose this is of initial condition with no load. So when we apply the load, it gets elongated. So we experience that the length is increased because of the elastic deformation. Now, if I keep on applying the load to this, what happens is these bonds will break and this point will come to the next lattice position. This will come to the next lattice position, and that is shown here actually. So here you can see there are 4 molecules in the first row, but now it is 3 when we apply the load. So what has happened is the molecule which was present here has shifted down. So similarly, the molecule which was present in the second row has moved to the third to the fourth, in this way the molecules has shifted, and this is not a reversible way. So this diagram, I want you to observe 2 things. One thing is, just now I explained that the molecules has changed their position from this to this, and this is permanent part. Second thing I want you to observe is this gap that is present. So gap is also present. So this gap is because of the stretching of the bonds that is present. Okay, so it is written like delta elastic plus plastic. So the delta which is caused because of this stretching of the bond is responsible for change in the length in the elastic, delta elastic, and because of the shifting of these molecules, the deform again there is an increase in the length, and that part is delta plastic. I hope it is clear. We have to understand this small things, but clear, we need to be clear with our basics. So this total deformation that what we are seeing here when the load is applied is combination of elastic deformation as well as plastic deformation. Out of this elastic deformation is caused because of this bonds, the elongation of the bonds, and the plastic deformation is causing because of the change in the position of the molecules. So you can see the molecules are shifting from the top to bottom layer. So if you pay attention, you will understand that if you have a rod like this and all the molecules from every layer are moving to the next layer, its length is definitely going to increase. But what is going to happen to its diameter? It is going to decrease because the molecules are shifting from this to this. So that's what we experience. So when we elongate something, we experience that its diameter is decreasing and the length is increasing. And the important thing to understand is total deformation is equals to elastic deformation plus plastic deformation. Now when we remove this load F, what is going to happen is this elastic deformation is going to vanish and this plastic deformation is going to stay. So this is the part that we are going to see, the plastic deformation. So that plastic deformation is because of the change in the position of the molecules, which we can't revert back. But this stretching of the bonds can be reversed when we remove this load. Okay. So same thing is explained here. This is the lattice arrangement, and this phenomenon is called as slip. Okay, just for your information, this when the molecules change from one lattice position to the next lattice position, that phenomenon is called as slip. Is it clear? Okay, so I hope this is clear. So same thing. Harshal is asking about the resisting forces in elastic and plastic bodies. We'll discuss this in some time. 1 minute. Elastic and plastic deformation. This is now we have seen. So what we understood from this is initially there is a elastic deformation, and when we apply load more than elastic limit, again there is a plastic deformation, and when we remove the load, elastic deformation goes and plastic deformation stays. Okay. Yes, same thing happens in rubber also. Okay. So we are going to see now stress strain diagrams. um, so in this I want to show one phenomenon here that is occurring. So this is, suppose this is stress versus strain or you can also say this as a load versus elongation graph. I will explain this thing, but just now pay attention. This is load versus elongation. That is also fine. Nature of graph will not change, only values will change, but I will explain you that part. 1 minute. So suppose this is load versus elongation graph. So what happens when we start loading it, more load we apply, we get, and we reach to a point which is called as elastic limit. Okay. So up to the elastic limit, we can load the component, we can unload the component. It will travel along this line. So when we load this, it will go in this direction. When we unload it, it will come back to its original position. So elongation is 0. So when you remove the load completely, elongation is completely 0. Once we cross this limit, elastic limit, we reach into the plastic deformation region. So this is all the deformation that is taking place after this point. This much of elongation is elastic deformation, and after this, whatever is happening on this side is plastic deformation. So here plastic deformation is taking place, and suppose after doing some plastic deformation, if I decide to remove the load, what will happen? It will not travel back like this, because not possible, because plastic deformation has already taken place, but it will travel something like this. Okay, so it will come back to this. So this deformation is always present because it is plastic deformation, but this much of deformation we have removed. So here total deformation was this much. Out of this much elastic deformation has been removed, and this much of plastic deformation is there. Okay, so what is happening at the molecular level? This is the elastic deformation. When we apply the load beyond elastic, this slip phenomenon occurs and plastic deformation takes place. And when we remove the load, the molecules come together, but they don't go back to their original position. Okay, so this is how the elasticity and plasticity works. Same thing is explained with some other graph. Okay. Now to calculate this and to study this behavior of elasticity and plasticity, to find out the values of elastic limit and all these things, we need stress strain diagram. And how to plot the stress strain diagram? There is one test that is called as tensile test. We'll watch this video. This video has explained this part.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100.
1 minute.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without
Okay, so what we have seen is something like this. Stress versus strain. So tensile test is very common, simple test which is performed. And this will give us this stress versus strain graph, in which we can see initially stress and strain. As the stress increases, strain is also increasing in a linear manner. So they are basically increasing in a straight line manner, and they are very proportional up to the elastic limit. and beyond the elastic limit there is a plastic deformation starts, and that is not linear in linear manner. So there is a very high increase in the plastic deformation up to the maximum tensile strength. After the maximum load is applied, there is a necking, and the stress will start to concentrate in the necking region, and then finally it breaks off. So this is how stress strain diagram is there. So this gives us lot many information that we will discuss in the next lecture. What are the information that we can get from this stress strain diagram? Uh, So I will take some doubts. The doubt is resistive force in elastic body and plastic body is same or different? It is different, definitely. In elastic body, the force is exactly equal to the applied load. In plastic, the internal resisting force becomes less than that of external load. So that's why there is a deformation that is taking place, plastic deformation that is taking place. Okay. Uh, how does the internal resisting force differs? That answers the same thing. So whenever there is plastic deformation taking place, the external force is higher than that of internal resisting force. So that's why the molecules are shifting from their position, because the force is higher than their resisting forces. And because now we are discussing this thing, all the design, whenever we design something, we need I will discuss on this diagram itself. So up to this point, the material is perfectly elastic. By elastic, what does it mean is when we apply the load, it will give exactly enough load to resist that. So what does that mean is, suppose there is some rod, and if I apply some 10 kilonewton of load, and which is less than its elastic limit, then 10 kilonewton of load will generate inside the body. How why it is called as load versus elongation? I will explain these things. uh, what is load versus elongation, because it is applied load versus the elongation. We calculate both the things. That is a simple thing. And if you take the load divided by area, and if you take the elongation divided by length, you will get load upon area is stress, and elongation upon original length is basically strain, sorry. So that is stress versus strain. Both these graphs are important for us, load versus elongation as well as stress versus strain. We can get different information from these graphs. We'll discuss those things. We don't have time now, but I will discuss those things afterwards. So what I'm saying is, whenever we design something, we want it to be somewhere here. So see this graph. So this is the point where elastic limit is there. And beyond this, the material is not capable of resisting the applied load in the same manner. So we want the design to be somewhere here. So we apply the load somewhere in up to this. We want to keep the stress up to this limit. We don't even want to go to the elastic limit. We want to keep it somewhere here, so that whatever is the load we are applying, the component will give us back the same. It will resist the same amount of load. Okay. Anything else? If you want to ask anything else. Okay. So this is the diagram that we have seen. Initially, it is a linear region in which stress versus strain is a linear manner. There is something called as proportional limit. We'll talk about this. Then there is a upper yield point, lower yield point, plastic deformation. Then there is a strain hardening region, necking region. So this is basically that diagram. This is actual diagram. The diagram what you have seen in the previous slide is not drawn to the scale. If you draw it something to the scale, it looks like this. That means important thing to understand here is, this is the elastic deformation and this is the plastic deformation. So you can see so much of plastic deformation is taking place. And this diagram is particularly for the mild steel. Don't get confused that it is for the all material. It is only particularly for the mild steel. So mild steel is undergoing a lot of deformation before the fracture. Before the fracture, it undergoes a lot of deformation. If the material is very soft like aluminum, it shows like this with no clear indication of it don't show any clear indication of end of the elastic limit or that like that. So what we do is we consider 0.02% strain as a proof strain, and then we draw a line parallel to this line, and where it cuts, that line is that thing is taken as a yield stress. But we don't call it as yield stress, we call this as a proof stress, 0.02%. If there is no perfect yield point, we get a perfect yield point for the mild steel, but we don't get perfect yield point for aluminum, copper, etc. If the material is brittle, the deformation don't go to the plastic region. So here initially it is a linear, then very small deformation, and then it breaks off. So the area under the curve is very small. If you compare it with the steel, it is like this, very large area indicating large amount of energy that is stored inside it. But for brittle material, that is not the case. It don't deform a lot in plastic deformation. It goes to some region and then it breaks off. If it is like glass, it will not even go to this region. It will somewhere break here itself. Okay, so time is up. So I will give you the link in the chat. You put your attendance. I have shared the link. So 1 minute. I have shared the link. You click this link and you put your attendance. Okay, thank you.